Alright, so welcome to this video. We're going to go through some of the applications of logarithmic functions and using the derivatives for those. So the first question I'm going to look at is around kinematics. So if we've got a particle, and we're going to call this particle P, moves in a straight line with the displacement function that looks something like this. S t is equal to 100t plus 200 e to the power of minus t on 5. So the first thing we're asked to do, obviously, let's actually define a few other things. That t is got to be greater than or equal to 0, and that our units are in this case, we're given to us in centimeters. So let's go through, and the first thing we need to do is find the velocity and acceleration functions. Well, if you remember from earlier video when we went through applications, that the velocity and acceleration functions are just the first and second derivatives of our displacement function respectively. So our velocity function, vt we'll call it, is equal to the first derivative of our displacement function. And what's that going to equal? So let's look at this first part here. Well, the derivative of 100t, so we're doing the derivative in respect to t. So the derivative of 100t is just 100. Then we're going to add. Now we're going to look at the derivative of this. Well, the derivative of e to the power of something is still e to the power whatever it is, but we take this, we work out our derivative of the power, and we multiply all of this by it. So minus t on 5, the derivative of that is just minus 1 on 5. So we're going to put that out the front using chain rule and multiply everything by it. So we're going to have minus 1 on 5 times 200 e to the power of minus t on 5. And this can be simplified further in that it's 100 take, now a fifth of 200 is just going to be 40 e to the power of minus t on 5. And this is in centimeters per second. And that's our velocity function. And now we just have to find our acceleration function, which is just the derivative of this, or our second derivative of our displacement function. So a t is equal to all of those, and that is a dash there, might be a bit hard to see. So our derivative of 100 is 0. Now same thing here applies. Our derivative of e to the power of minus t on 5 is still minus 1 on 5. Minus 1 on 5 times minus 40 is just 8. Positive 8 because it's multiplying two negatives together. E to the power of minus t on 5. And this is centimeters per second per second. Or we could write this as cms to the power of minus 1, cms to the power of minus 2. Alright, so that's our first one. We've got our velocity and acceleration functions. So we need to find the initial position, velocity, and acceleration of p. So to find these, we have when time is equal to 0, because that's our initial time, we're going to have S0 to find our initial position. going to be equal to 100 times 0 plus 200 e to the power of minus 0 on 5. Alright, so what's this going to equal? Well, 100 times 0 is just 0 plus 200 e to the power of minus 0 on 5. Now, but if we've got anything to the power of 0, which this will be equal to, this whole thing becomes 1. So it's going to be 200. Because e to the power of e to the power of 0 is just 1. So 200 times 1 is 200. And we'll say that this is to the right. And we'll say it's to the right. We should actually put in centimeters to the right. We'll say it's to the right because if we take from our origin being 0, anything that's positive is going to be to the right, anything that's negative is going to be to the left. Alright, so the next one we have to, what's its initial velocity? Again, when t is equal to 0, we're going to have 100 minus 40 e to the power of minus t on 5. In this case, t is actually 0, so let's change that to a 0. So, 100 minus 40 times e to the power of 0, which is just 1, so 100 take 40 times 1 is just 100 take 40, which gives us 60. 60 centimeters per second. And we'll say that this is to the right too. Alright, our final one, acceleration. Again, when time equals 0, it's just going to be equal to 8 e to the power of 0 on 5. So again, e to the power of 0 is just 1. So 8 times 1 is just going to be 8 centimeters per second per second. So we've got that bit of information now. So we've got our initial conditions on what this particle is doing when time is equal to 0. The next question that gets asked, discuss the velocity of our particle as t approaches infinity. So what does the velocity do? So looking at this function here, what does t, when t keeps getting larger and larger and larger, what happens to this function here? What does v tend towards? Well, let's think about it for a moment. We've got e to the power of a negative number. So really, we could rewrite this as being v t is equal to 100 minus 40 divided by e to the power of t on 5. So as t increases, this whole thing's going to keep increasing, which is going to make it smaller. And this is going to keep getting smaller and smaller and smaller and smaller. So until eventually it becomes virtually nothing. So we could say that as t heads towards infinity, then Vt is going to head towards 100 because we can have 100 minus nothing. And we could say that this is from below. And the reason it's from below is because we really kind of have this horizontal asymptote at 100 for our velocity time graph. So it's going to come up to and get very close to that, as you'll see in the next part, which is sketch the graph of the velocity function. So let's change color. And I'm going to go right up top here. That's probably the neatest I'm going to get that. So let's go like this. Here we have time, and here we have our velocity. Alright, so let's put in some points. So we're going to have here at 100. Our initial starting position was 60 centimeters, or initial velocity was 60 centimeters. So let's put another point in here at 60. And what we're going to do, we're going to find that, as I mentioned before, there's this vertical asymptote here. As this function, as time increases, what's going to happen is this is going to get closer and closer and closer and closer to 100. It'll keep getting closer and closer till virtually it's going to be 100. So that's our graph. So we're just taking some of the information we know to sketch it. Our final part is find the time at which the velocity of the particle is 80 meters per second. So got Vt being equal to 80. And we need to find out what t is equal to. We don't know yet. So we're going to have to use logarithms on our velocity function and find out and solve for t. So let's set it up. 80 being equal to 100 minus 40 e to the power of minus t on 5. Let's rearrange this and make things a little bit better to start with. So we'll collect our 80 and 100 together, and we'll find that the minus signs disappear. So if we take 100 over here, we've got minus 20 equal to minus 40 e to the power of t on 5. So it's just really the same as 20 equals 40 e to the power of t on 5. Now I have to solve for t because we want to know at what time is the velocity equal to 80 centimeters per second. So we're going to take the natural log of both of these sides, and you'll find that the natural log of e to the power of minus t on 5 will just, the natural log and e will cancel the e out, and we'll just be left with this power term here. So we have the natural log of 20 equal to, and we'll use our log laws here. So we have the natural log of 40 plus natural log of e to the power of minus t on 5, which is equal to, and we'll take this over here, so we've got natural log of 20, take the natural log of 40, using our logarithmic laws, is really just the natural log of 20 over 40. It's equal to minus t on 5. So this is really the natural log of a half, so I've got natural log of 1 over 2, and we're going to multiply that by 5. It's going to give us minus t. Now, the natural log of a half is a really small number, and it's also negative. So punch in your calculator as the natural log of 0.5, and you'll find that it's negative 0.693 with lots of numbers after it. We'll multiply that by 5, and we'll find it's still a negative number, so we've got negative and negative, so they'll become positive. We'll find that t is just equal to, or close to, 3.468 seconds. And that's our answer. So we're using logarithms and derivatives to solve some problems in terms of kinematics. So that's an example from kinematics. I'm going to do next a example from rates of change, and then I'll do an optimization one as well. So let's look at the rate of change one.